Welcome everyone to today's Intro Algorithms Explainer. Today we are taking a really fascinating journey into the world of dynamic programming. Now, if you've ever felt completely overwhelmed by optimization problems that just seem to grow exponentially complex, well, you're in exactly the right place. We're going to tame all that complexity by looking at a classic computer science case study, the rod cutting problem. So, grab your virtual notebooks because we're going to break this whole thing down, step by step.
Here is our game plan for today. We'll start with the dynamic programming paradigm, then introduce our case study, the rod cutting problem. From there, we'll compare recursion and memoization, build out a bottom-up array, learn how to reconstruct the actual cuts, and finally, finish up with a few practice scenarios.
All right, Part 1, the dynamic programming paradigm, or, as I like to think of it, saving solutions for reuse.
Okay, let's jump right in. Dynamic programming is a brilliantly efficient method used specifically for optimization problems. The core idea here is really simple, but is incredibly powerful. We use this approach when our subproblems share subproblems, meaning instead of solving the exact same pieces of a puzzle over and over and over again, we save our solutions for reuse. According to our source textbook, there are 4 fundamental steps to this methodology. Step 1 is to characterize the structure of an optimal solution. Step 2, we recursively define the value of that optimal solution. Step 3 is to compute the value, typically in a bottom-up fashion. And Step 4, we construct the final optimal solution from those computed optimal subsolutions. That's our basic blueprint.
Moving on to Part 2, the rod cutting problem, where it's all about maximizing revenue. Let's see how our blueprint builds into a tangible scenario. Picture this. You've got a steel rod of length n inches and a master price list. A length of 1 inch sells for $1. A length of 2 inches sells for $5. A 3-inch piece is $8, and so on, all the way up to a 10-inch rod which sells for $30. The problem we have to solve is this. Given a rod of length n, how do you cut it up, or do you cut it at all, to determine the absolute maximum revenue obtainable? Look closely at the prices here. Sometimes the absolute most profitable move is to make no cuts at all. For example, a 10-inch rod sells for $30, but if you cut it into 2 5-inch rods, well, those only sell for $10 each, totaling $20. You've literally just lost $10 by cutting it. So we need an algorithm to figure out the best combination every single time without guessing.
Part 3, recursion versus memoization, and the massive cost of redundancy.
Think about the trap of a naive approach here. If we just use basic, top-down recursion for a rod of length 4, the computer asks, okay, what's the best price for 4? To answer that, it needs to figure out the best prices for 3, 2, 1, and 0. But look at what happens when it evaluates length 3. It has to independently evaluate length 2, 1, and 0 all over again. This computation tree just explodes. Subproblems are being calculated completely redundantly. In fact, the total number of calls grows exponentially, specifically at a rate of 2 to the power of n. Now, for a 4-inch rod, sure, it's manageable. But for a 40-inch rod, your computer might literally be running until the end of the universe.
So how do we actually fix all this overlapping work? Enter top-down memoization. It's essentially the exact same recursive approach, but we give it a memory bank. We create an array R to store our maximum revenues. Before the algorithm does any of the heavy lifting for length n, it simply checks, is the value in R at index n greater than or equal to 0? If it is, boom, that means we've already solved this subproblem. We just return the saved answer. This single aha moment of checking a memory array drops our time complexity dramatically, just because it prevents us from repeating previously solved work.
All right, Part 4, building the bottom-up array through orderly tabulation.
Now, top-down memoization is fantastic, but there's an even more systematic way to do this, the bottom-up approach. Before we build our array, though, we need our optimality formula. And this formula brilliantly illustrates the sheer elegance of dynamic programming. Basically, the maximum revenue for a rod of length n is the maximum value of the price of an initial cut plus the optimal revenue of the remaining piece. We check this for every possible initial cut from length 1 up to n. We are quite literally breaking the rod into 2 pieces, a piece we sell immediately from our price sheet and a remainder piece whose optimal value we've already calculated and saved.
Let's actually build this table from the ground up to see how it works in real time. We start at the absolute bottom. A rod of length 0 obviously yields a revenue of 0. For length 1, we look at our price sheet. It's $1. Easy. Now, length 2. We could sell it as a whole 2-inch piece for $5, or cut it into two 1-inch pieces, which would be $1 plus $1, so $2. The max there is $5. We store that. For length 3, the best is selling it whole for $8. For length 4, we evaluate our options, and the best move is actually cutting it into two 2-inch pieces. And since we already stored the optimal value for a 2-inch piece as $5 earlier, we just do 5 plus 5 equals 10. We systematically compute these values from size 0 all the way up to n, meaning every single calculation only ever relies on previously saved optimal answers.
And if we keep following this bottom-up tabulation all the way to index 10 using our original price sheet, our array fills up beautifully until we reach our final slot. The maximum revenue for a length of 10 is 30. We've completely solved the optimization problem, and we didn't do a single redundant calculation.
Which brings us to part 5, reconstructing the actual cuts using an auxiliary array.
Knowing the maximum revenue is awesome for the accountants, sure. But if you're the worker on the factory floor, how do you physically cut the rod to achieve it? To figure that out, we use the extended bottom-up cut rod algorithm. Alongside our revenue array, we maintain a second auxiliary array called S. So what does S do? Well, every time we find a new maximum revenue for a given length, we save the size of the very first piece we cut off to achieve that maximum. So index I in our S array simply stores the optimal size of the first cut for a rod of length I. This little auxiliary array makes the final step almost absurdly simple. To print out the actual optimal cuts, we just use a basic while loop. While our rod length n is greater than 0, we look up our S array at index n, and that tells us the exact size of the first piece to chop off. Then, we just update our remaining length by subtracting that piece. And we repeat the loop. It's a perfect, foolproof set of instructions.
Let's ground this with a real example. Say we have a rod of length 7. If we consult our auxiliary array for a length of 7, the value is 1. So our first cut is a 1-inch piece. We subtract 1 from 7, leaving us with a remainder of 6 inches. Now we loop back and look up the value for a length of 6. The array tells us it's 6. That means our next piece is 6 inches long. 6 minus 6 is 0, so the loop ends. Our optimal cuts are a 1-inch piece and a 6-inch piece. If we double-check our original price table, a 1-inch piece is $1 and a 6-inch piece is $17. Total revenue is 18. Perfectly optimized with absolutely zero guesswork.
Okay, part 6, practice scenarios. It is your turn.
All right, class, time for a quick pop quiz to see if this bottom-up process is really clicking for you. Using the initial price table we looked at the beginning of the explainer, I want you to mentally reconstruct the bottom-up array. What are the optimal cuts and the maximum revenues for rod lengths of 2, 3, and 4? Take a second to think through the logic. And remember, sometimes the best cut is no cut at all.
All right, let's dive into the results derived straight from our source text. For a length of 2, the optimal revenue is 5. We achieve this by making no cuts. We just sell the 2-inch piece whole. For a length of 3, the optimal revenue is 8. Again, our solution tells us 3 equals 3, meaning no cuts. The price sheet naturally favors the whole piece here. But a length of 4 is where dynamic programming really shines. A whole 4-inch piece only sells for $9. But because we saved the optimal answer for a 2-inch piece earlier, which was $5, our algorithm sees that 2 plus 2 yields a revenue of 10. So for length 4, the optimal strategy is definitely splitting it into two 2-inch pieces.
And you know, this brings us perfectly back to the elegant philosophy of dynamic programming. The value of an element is simply the maximum of the price of an initial cut plus the remaining optimal revenue. By carefully characterizing the structure of the optimal solution, defining it recursively, and then systematically calculating it from the bottom up, we literally turned a nightmare exponential problem into a smooth, orderly table of answers. We broke the problem down, and we built it back up with saved solutions.
So I'm going to leave you with this final thought today. If merely saving our answers in a simple array can tame the exponential beast of the rod-cutting problem, what other massive computational roadblocks could dynamic programming help us demolish? From sequence alignments in DNA to optimizing global supply chains, the ability to store and reuse overlapping subproblems is without a doubt one of the most powerful tools in all of computer science. Keep exploring, keep optimizing, and I will see you in the next explainer.